So today we continue to talk about identical particles, and we're going to begin with 5.1.3, which is spin. You might realize that in my previous video and the video before, I talk about in my previous video specifically I talk about the symmetrical and anti-symmetrical aspect of wave function in terms of spatial coordinates r1 and r2 for two particles, right? How when they swap, they're either symmetrical, so positive, or anti-symmetrical. So in the case of positive, like you have two bosons, this would be, right? Just a quick little review that this is what we meant when we say identical particles, in this case boson for positive, are symmetrical under exchange. And for anti-symmetrical, so in this case the fermions, we're gonna have a negative sign in front of the side for R2, R1. This is anti-symmetrical. Symmetrical. Boson, fermion. And one thing I did not talk about was spin. So the complete state of the electron, so it's not just phi with respect to r, like the spatial coordinate is not the complete information to our wave function. There's also something which we call the spinner, which we can write as x here. And when we have two particle states, so psi r1, r2, similar as before, we have x 1 and 2. So it is the whole work, not just the spatial parts, that has to be anti-symmetric with respect to exchange. So let's write down the formula and take a closer look. So when I have phi r1, r2, x spinner here, 1, 2, this is going to be equal to negative phi r2, r1. So we're looking at the anti-symmetrical case here. And the spinner here is going to be 2, 1. So what does this mean? This means that when we have two particles, so two identical particles that are anti-symmetrical under exchange. So in this case, fermions, because fermions are anti-symmetrical under exchange. When you swap r1, r2, the spatial two coordinates, the 1 and 2 in the spinner must also swap. And for bosons, since they're symmetrical under exchange, then we have something that looks like this for boson. So imagine we're dealing with bosons right now, then this would be R2, R1 with no negative in front of it. So fermions, bosons. And what's very interesting about the anti-symmetrical case here is, let's copy and paste this and move this down. So copy, and then I want to paste. So what we have here, what's very interesting is that if phi r1, r2 is symmetric, then x 1, 2 must be anti-symmetric. And there's a reason for that, because remember, for r1, r2, if it is anti-symmetrical, it implies that it is equal to negative r2, r1. Right, so for the case of fermion, if let's say your phi r1, r2 are anti-symmetrical, so you will end up with something like a negative over here. But the same rule goes for the spinner. So if I have the spinner 1, 2, 1, 1, 2, if the spinner is anti-symmetric, this will result in negative under this exchange, right? So if they're both anti-symmetrical, then what ends up happening here? if both of these are antisymmetrical. Well, if both of these are antisymmetrical, then you end up with negative by R2, R1, and negative x, 2, 1. So you have two negative, and you multiply them to each other, that makes the positive, right? So that cannot be right, because the system or the total wave function must be antisymmetric under the exchange. And this cannot be right, because if both of these are antisymmetrical, you end up with something positive for fermion. And in this case, if they are both antisymmetrical, then you will end up with something like this. But this cannot be right? Because this expression is for bosons, not for fermions, and bosons are symmetrical under exchange. So therefore, for antisymmetrical, if the spatial R1, R2 is symmetric, then the spinor X12 must be antisymmetric, or the other way around. If the spatial R1, R2 is antisymmetric, then the spinor must be symmetric. And for our fermion here, the spinor has two states, which we call the singlet state and the triplet state. I think this part of the material is indeed from chapter 4, but just to refresh the memory here. The singlet state. Okay. The singlet state. Singlet state. So in the singlet state, so x12, this is going to be equal to 1 over square root of 2. Spin up, spin down, minus down, up. And this is anti-symmetric spin. You could tell because of the negative sign in between them. And there are also the triplet state. Which is x12 is equal to 1 over 2 up, down, plus down, up, right? Plus would indicate this is symmetric spin. And for the triplet state, there are also case where both particles have spin up and both particles have spin down. So the triplet state consists of these three, and the singlet states consist of that. So back in the chapter 4, the singlet states are antisymmetric, and all the three triplet states that we have here are all symmetric. So thus, the Pauli exclusion principle, if you remember what I talked about in my previous video, actually allows two electrons in the given position state, as long as their spin are in the singlet configuration. That means that you could have two electrons in the same state. One is spin up, the other one is spin down, or the other way around, it would work. But they could not be in the same position state, so you cannot have a electron with 1 over 2 spin and another electron with 1 over 2 spin occupy the same position state. Or you also cannot have, if let's say both are spin up and both are spin down, that doesn't work too. So two electrons can share the same spatial position state, but their spin must be in the singlet configuration, which is what we have here, and cannot be in these three. So let's move on to the next part. The next part video, I'm going to talk about 5.1.4, which is the generalized symmetrization principle. So this part is pretty short, so I'm just gonna go through it quickly. So suppose we have some operator which we call exchange operator P. So exchange operator P. And what exchange operator does is that it interchanges two particles. So when you apply a exchange operator to 1, 2, it changes it, or it swaps, in other words, exchange the particles. So this is what exchange operator particles do. It interchange two particles. So clearly, the exchange operator square is going to be 1, right? Because when you apply exchange operator to 1, 2, it becomes 2, 1. Then if you apply exchange operator to 2, 1 again, it goes back to 1, 2. Right? So when you apply the exchanger itself 2 times or square it, it's going to be equal to 1. So there's no change. That's like saying if I'm not sure if I should talk about this example, but imagine you have the y-axis, x-axis here. If there's some operator that changes this arrow to here, right? That operator square is going to be 1, 2, because if it changes here, that's the first change. Then if you apply the operator to this right here, it's going to change back, right? So there is no change when squared. So therefore, our exchange operator square here is going to be equal to 1. And know the eigenvalue of our exchange operator are going to be 2b plus minus 1. This is because of what we've been saying this whole time, is that the idea of symmetrical and anti-symmetrical, because when you apply our exchange operator to a psi 1, 2, this could be either psi 2, 1 or negative psi 2, 1, right? In the case of this is symmetrical, this is anti-symmetrical, and in this case, P is going to be equal to negative. The eigenvalue of P is going to be equal to negative 1. The eigenvalue of P here is going to be equal to positive 1. Not sure if you guys still remember the eigenvalue, all the eigenvalue stuff, because sometimes I forget them too. But here I remember, if you have I think the formula was AV is equal to lambda V, right? So imagine our A is the P here, our V here is our wave function. You can clearly see your eigenvalue here. Lambda could be either 1 or negative 1. So that is why the textbook said the eigenvalue of exchange operator is going to be plus minus 1. Now, very importantly, if the two particles are identical, the Hamiltonian must treat them the same. Because remember that Hamiltonian, for the same mass, we need to make sure the mass is the same, because that influences the kinetic part of the Hamiltonian. So if mass is the same, they're identical, then the potential should be the same too. So V R1 R2 T is going to be V R2 R1 T, right? So the Hamiltonian treat them the same. If the Hamiltonian treat them the same, then the potential energy is symmetrical on the exchange, right? There is nothing. The potential energy is not changing if you swap spatial coordinates. And it follows that. So exchange operator P and Hamiltonian. So and Hamiltonian are compatible observables. In other words, P H is equal to 0. So what does this mean? Well, if you expand this, this really means pH minus HP is equal to 0. So the commuter here measures how our exchange cooperator and the Hamiltonian interact. What this says here is that if this is equal to 0, then it means that when we apply our exchange operator to our Hamiltonian, it does not change the Hamiltonian, right? That sort of makes sense. So the Hamiltonian describes the energy of the two particles, and when you exchange the two particles, the Hamiltonian does not change. So the first one, this means applying our exchange operator does not change the Hamiltonian. And the second one goes the same way. If we apply the Hamiltonian to our exchange, it doesn't change anything. Like, what's like a right way to put it? Maybe it's that Hamiltonian respect the symmetry of the system under particle exchange. I think if you get the idea of what's happening here with the pH, you get what's happening here with the HP. But it basically these two are two operators, and when one applies to the other one, that doesn't change anything, and vice versa. So that's what's happening here. So therefore, we have the commuter as 0. And another very important thing to talk about is, so first of all, if we have some operator O, the time evolution of the expectation value of operator O, so d dt, so time evolution of our operator, the expectation value of our operator for these brackets, right? Expectation of our operator O is given by the formula I H Hamiltonian O plus our partial O here. So for P, this is going to be equal to 0 because it has no explicit time dependence, right? Our exchange operator does not depend on time. So this term is going to be equal to 0. Well, let's write this in this form first. So for exchange operator P, this would be IH Hamiltonian P right? This is going to be equal to 0 because of the reason I just explained. And then this part is going to be equal to 0 as I have just explained here, right? So this is going to imply dt of the excitation of our exchange operator is going to be 0. So what does this mean? This means that our exchange operator is constant in time. It implies the symmetry of the wave function under exchange is preserved over time. And in other words, as time goes on, this exchange operator does not change. And that is just the property of our exchange operator. Another very important thing about our system is that if a system starts out in an eigenstate of P, either symmetric or antisymmetric, then it will stay that way forever. So if your systems at the beginning was symmetrical, it will never become antisymmetrical, and vice versa. When the system started out, if it started out as antisymmetrical, it will never become symmetrical at any point, right? Because of the reason we have just listed. Because that the exchange is preserved over time. right? So they don't, so the starting point of your system does matter. And the symmetrization axiom says that for identical particle, the state is not merely allowed but required to satisfy this formula. Plus minus what this really means is that it just means that when you swap the particles, it must either always be positive or negative, depends on your situation. Symmetric for positive, asymmetric for negative. Like, it just says that mathematically a system has to be either symmetric or asymmetric. That's all this says, and nothing more. And since it's the same for two identical particle system, it must also be the same for n identical particle system, for n identical particles. So a more generalized formula would be the same formula that we have here, but for n particles. So 1, 2, I, j, n is equal to plus minus. So what this says is that it applies to, so what we have done for these two identical particles, it's the same that applies to n number of identical particles too. So for n identical particles, the system must be either asymmetrical, antisymmetrical, or symmetrical. Just like our identical two particle system. And this is a general statement, and is called the generalized symmetrization principle, which says that when you have n identical particles, the system must be either symmetric under exchange or antisymmetric. That's it. There's nothing more to it. And that will be it for this video. If you guys have learned something, feel free to comment down. If you guys have any questions, feel free to comment down. And I'll see you guys on the next video.